good to go.
All right. Anybody did I collect all the assignments or do I still have some assignments? I know you don't have one. Anybody have the volumes thing to turn in to me? Or got them all?
I'll turn mine in Wednesday.
Okie doke. Did you forget about it?
Yeah.
Okay. First, can you get it to me at the start of class on Wednesday?
Yeah.
Okay. PK, yeah, I'll get you the assignment. I just gotta get you the details. All right, we're starting a new unit. There's a new web work that's opening up. This web work is entitled Differential Equations, because that's what we're going to talk about. And probably for the scientists in here, this is probably the most important thing you'll learn this semester. And then it's one of the tops, definitely one of the tops. So in this assignment, which is due next Wednesday, It might be due Sunday. We'll see how it goes. I think we can get it done this week. The first two problems are actually volume problems. So the first two problems are volumes of rotation. And so I know I told you there wouldn't be any, but there's just two. Web work. I know. I'm trying to help make it less terrible for you. I know. You'd probably prefer I just not even talk about it, but. So the first two problems on here, actually find the volume. You have to come up with a number, so you have to do the integral. And then after that, I think at the end of today, the third problem should be something you can do. But I hesitate to set you loose on the rest of this. So after today's class, the first three on that assignment should go well. I'll let you know if you can move further. I don't know if I even need my notes. So, differential equations. Anybody encountered these before? Anybody ever done any stuff with them? Very quiet.
I just know it's Calc 3, that's it.
What's that?
I just know that's like the Calc 3 course, but I don't really know what it is.
Okay, we don't know. We're not quite sure here. All right, well, in the rough sense, this is basically just the language of science. That's all, just a little thing. They say math is the language of science, but this is really the language of science. And let's, the reason is, here's kind of the plan that a scientist would use, or the flow that a scientist might proceed along. You make some observations about a system, or a system, or I don't know why I'm coming up, just a problem. You get some data. And from that data, you hypothesize a relationship between some variables. So this is kind of step one, using one, hypothesize, and this is going to be a little different than you might hypothesize a relationship between the data and the rates of change of the data, between data points and things that are changing in the data. So this is all about putting together rates of change, maybe velocities, maybe accelerations, and maybe even things beyond that, right? Like the third derivative is called jerk, which is always weird, but relating rates of change and things that are changing. So between data points and things that are changing. So let me show you what I mean in particular. So let's start with an example. This will be a cool one. We'll just start with radioactive decay. So that everybody knows something about, right? We know that a radioactive substance, if you take it, it's really dangerous because shit is flying off of it. And all that stuff passes through your bodies and causes cells to mutate. So let's start with a block of strontium 738, I think. Now I do want to look at my notes, because I think I had a particular strontium, and maybe you guys can help me out here. I guess it doesn't really matter for what I'm about to say here. I feel like I want something from my physics friends. I want something that you can go, oh, remember that day he did science? That was a good day. Yeah, I don't have it here. So let's start radioactive decay. So I've got a block, and I'm just going to say, I'll say strontium 738. Why not? Strontium, and I'm going to put 738 even if I have no idea if that's actually a number. This is radioactive. Big block of stuff that's deadly. Stay away. Geiger counter's going off. When I first got to Regis, the old physics professor, the physics department was in the basement of the science building. And it was a pit. It was an incredible pit. And down there was every piece of ancient physics theory you could ever imagine. And one of the things they found, that the physicist died of cancer, who was here before Dr. Gray, which is terrible. And one of the things they found in his desk drawer, the middle desk drawer, was a giant block of radioactive material. So he would go sit at his desk every day with a block of radioactive material, pretty much right over his crotch. This is like blasting himself day after day. So we've got, this is that block that was in there. Oh my God, so dark.
Wait,
I'm sorry.
Did he purposely have that there?
We don't know.
Oh, were
Like
you,
Dr.
that was our,
Yes.
were you here teaching when this happened?
Yeah.
That's crazy. How long's Dr. Gray been here?
A little less than me, but close. I've been here like 16 years.
That's crazy.
7 to 6. I got here in 2009, so 15. A long fucking time.
Multiple undergraduates worth.
Multiple undergraduates worth, yes. Some of the original graduates I know are like have kids and they're just crazy. And they're professional adults and stuff like that. Not that you're not professional adults, but you're stuck in college. You don't get to make money like a professional adult. So, what is the half-life of the radioactive material? What does that mean? Can somebody tell us?
How long gets radioactive for?
Yeah, it takes what to decay? These are both right, but they're not precise enough. What is the half-life? I said the half-life of strontium 738 is 10 years. What does that mean?
In 10 years, it'll be exactly half the radioactivity it is right now.
That's it. So, right ideas. I just wanted that precise. So let's say it has a half-life of 10 years. So that means in 10 years, if we start off with 1,000 grams of the strontium, I'm going to have half that much. So I have a slightly smaller amount, not necessarily a cube worth, but I've got 500 grams of it in 10 years. So this was a 10-year stretch. We wait another 10 years. After another 10 years, how much strontium do I have?
250.
250, got half that, right? So I've got an even tinier cube of strontium. I'm doing a pretty good job of making these cubes look relatively halves of each other. Everything okay? So, no? Okay.
No, that's fine.
Okay, cool.
Just remembered something.
So what I want to think about here is the change in mass over the change in time. So here the mass is 1,000 grams, 500 grams, and 250 grams. So let's look at the change in mass over the change in time. So in this block right here, I ended up with 500. I started with 1,000, and that all happened over a 10-year period. So that's negative 50. Negative 50 grams per year. That's the average rate of change about how much strontium I'm losing. It's not the exact amount, because I'm losing at a faster rate toward the beginning and less toward the end of that period, which maybe isn't obvious yet, but that's what I hope to make obvious. And then in this next window of time, so this is delta m over delta t. Over here, we've got delta m over delta t is equal to the end, 250 grams minus the start, over the same period of time, 10 years. So that turns into negative 25 grams per year. Is that all making sense? Check it out, make sure that, yeah. Cool, okay. Good, Kellen? Yeah. Thumbs around? All right. Cool. So notice that the rate of change is changing itself, right? The average rate of change here was negative 50 per year, negative 50 grams per year. Rate of change here was negative 25 grams per year. What would actually be the rate of change in the next 10 years? So 30 years from now, I'm in the ground, you're at my gravesite, honoring me with this cube of strontium that killed me. 125 grams. You come up and you're like, this killed him. You throw it into my grave. It's whatever. So change in mass or change in time here is what?
250 minus 125 over 10.
Yeah, let's start and
Yeah,
so
yeah,
in
yeah,
the
120, other way around.
Yep.
Yeah.
just so we have the flow, because we want to decrease, right? It's
That
actually,
makes sense, yeah.
and then so what is that? That is negative 12.5. Yeah, grams per year. So notice how the rate of change is changing itself, and it's really dependent upon how much I started with. Does that make sense? See if you see that. So when I started with 1,000 grams, this was the change over the half-life. When I started with 500 grams, this was the change, and when I started with 250 grams, this was the change. We could almost come up with a rule for it. We could actually probably figure that out pretty easily. So a physicist would look at this, and this is undoubtedly what a physicist did, and they said, okay, let me assign some variables. Let me let m be the mass of strontium at time t, or whatever, a substance, the radioactive substance, at time t. And then I'm going to say the rate of change, so dm dt is equal to the rate of change of the mass at time t. This is a function of t, of course, at time t. Does that all sound like, notation-wise, we understand what I'm saying? Derivatives are rates of change. I hope we got that, because that's Calc 1, and we're deep into Calc 2. So what a physicist might notice is that, and I'm going to use a little bit of notation here, I'm going to use m dot instead of m prime. That's just derivative with respect to time. So think of that as y prime or whatever. That's dm dt, not dmt, dm dt. So that is m dot equals, the rate of change is proportional. I'm going to toss a k in to the mass that I have. The rate of change of the mass is proportional, this k I don't know, to the mass that I have. And that'll determine how fast the thing is changing.
What is the K supposed to represent?
It's a constant, I don't know, it's a constant of proportionality.
Okay.
So it's an unknown right now.
Is it unitless?
Yes. Probably not, because this is going to be grams per second. This is just grams, so this is something per second.
Okay.
But it's a constant that would change depending on the substance that I was looking at. So if something decayed faster, this might be a larger number. Something decayed slower.
Are you able to define K as something? I don't understand what K is representing.
It's just simply a constant of proportionality. I don't know what it is yet.
It's just a
Like
variable.
right
But what does
here.
it do?
Well, it allows us to handle different substances. So notice here that I could say this rate of change here, Alexander, how much did I start with? I started with 1,000, right?
Yeah.
So here, delta m, delta t, and I can't go to derivatives here because these are big stretches of time, not instantaneous rates of change. That's what that's all about. dmdt is equal to, what number do I have to multiply it by to get this number here? So, let's see, our current mass is 1,000, so this is m. What would k equal here? Well, the rate of change was -50, so for this first period of time, the k is equal to -20. No, what am I talking about? It's -50 over 1,000, whatever that is. So all I'm saying is that the rate of, I don't know what K is. I can't know because it depends on the substance and I have to actually solve that differential equation to figure it out anyway. It'll come out in the wash. So you start off with it as an unknown. All I'm trying to say is the observation, don't worry about what K is. Do you agree that the rate of change is proportional to the mass, just based upon that?
I do.
That's all I want to say.
Yeah.
And we can find K when we need to. And we will at some point. So this is a differential equation. It relates a rate of change of a variable m to the variable m itself. So check this out. This is really different than this. If I gave you this and I said dmdt is t squared. That's not m. This is relating m, the rate of change of m, to an independent variable. This is relating the rate of change of m to the state of m itself. Like this one I could solve. This is just m equals the integral 1/3 t cubed plus a constant. This is not that easy to solve. So here we have a differential equation, but I need one more thing to come with it. And I'm going to show you how to solve this. And we can actually go through, we'll solve this freaking problem. We'll solve this problem a little later. Might not be till Wednesday. This is a differential equation relating a rate of change to the state of the system. And the state of the system here, we're just observing the mass. Let's do a different one. Let's do another one. Let's say I've got a jar, a little petri dish filled with critters that are very tiny and need a microscope to grow. You can see I'm not a biologist. So let's say I've got a petri, but I can draw a petri dish because that's just a disc that was cut from a calculus object as we rotated it. So here's a petri dish. And inside here I've got some agar and stuff, blah, blah, blah. And I'm gonna put in there one little bug that can split. What's something that can split?
A cell.
Yeah, sure, that sounds good. A cell. This is also freaking vague. That sounds perfect. So put one cell into the dish. We watch and we watch and we watch, and we notice that at some point there's 2 cells. Oh my God, it grew. Wow, we picked the right agar and everything. And we did it, we kept it at the right temperature. So let's say after 10 hours, there are 2 parameciums or whatever the heck is in there. There's 1, there's 2, so there's the 1. See, I put him in there. Now there's 2 critters, 2 cell critters in the bowl. How many cell critters are going to be there after another 10 hours passes?
4.
Yeah, there you go, because they each doubled, right? Yeah. So this is the reverse of radioactive decay. This is the doubling life, 10 hours. So after 10 more hours, I've got 4 cell critters in the petri dish, and so on and so on. Now 10 hours sounds pretty long for this. I don't know, does anybody know biology well enough? Yeah. What's a time for, what is that, what do you call that process? Mitosis?
Well, I think so, but like usually when I would incubate plates, they would take between like a day to a week.
Yeah.
Oh, really? Okay,
takes
so
a
this
while.
is super fast.
Yeah.
Okay, cool. Okay.
So I was thinking about like working with C. elegans. It takes about a week.
Okay, oh, cool. Let's do that. So 1 week. I like it. So let's say 7 days. Yeah. Just to have something that's not just a 1. So another 7 days. Yeah. Cool. Thanks. Thank you. Thank you, gentlemen, for your expertise. Fantastic. You are truly the experts in this. And so, what was our question? A of t equals the number of cell critters in the dish at time t. All right, let's just take a look here. So what I've got here is the change in A in this first period. The change in A, or the change in time, is going to be, I guess, just, that's a little rough, isn't it? Because it's like the difference. Yeah, whatever. Okay, it's all good. So it's going to be 2 minus 1 over 7 days. So there's 1, roughly, the average is 1 every 7 days. It's kind of, yeah, I don't know. This is going to be a little rough. So people who understand this stuff, give me a little slack. It's going to be weird. It's going to be bullshitty. That's okay. We're used to that. And then, so this is during the first period, in the first 7 days. And then in the second 7 days, the rate of change of A over the rate of change of time. Now it's different because I've got 4 minus 2 over 7, so it's actually twice as fast. The rate of change in the number of critters in the dish is increasing. The more critters that are there in the next 7 days, I'm going to have that many more. So what I want to observe here, I'm not going to keep going on with this because it's just ridiculous. Observe, exclamation point, the rate of change in the number of parameciums, whatever, is proportional. Now I don't know the proportion, but I'm just noticing that it depends directly upon the number that I started with. That's all I'm trying to say there. What's going on? What happened?
I was gonna throw this away.
Oh, okay. You can walk in front of it. We had Jose's head in front of it for like 3 hours. Okay.
Yeah, my bad.
No, it's not your bad. It's my bad. Like I said, I saw your head in the way when I did it and just didn't care or something. I don't know what it was. So look at this. Another differential equation. Does it look remotely familiar? It looks a lot like that one. So here we have radioactive decay, we have exponential growth, and they are both modeled by the same thing. So a biologist, a mathematical biologist might say, I'm going to try this model, that the rate of change of the rate of change in the population is this. And then I'm going to solve this and see if I come up with a formula. So our goal is going to be use these observations to create equations that relate rates of change to states, and then solve them and get a formula. And that's our goal. Yes, sir?
So A is the initial we start with. Like
Say that again.
A slash delta A is like just the value of A represents how many cells or whatever
Yeah.
you're starting with.
Or just they're in there at a moment.
Well,
Yeah.
Right. So
Yes.
so when you say like it's proportional to the starting amount, that A after like so you
Yeah.
see what I'm saying? That's like would be 2 in there, 1 in this case.
Yes. Yes. Yeah. Exactly. Yeah. Yeah. So I also usually want an initial condition. So I'm going to put here A at time 0 was 1. Over here, I might want an initial condition on this differential equation. I would say the mass at time 0 was 1,000 grams. So now I've got an initial condition. We're going to be able to solve both these. This one I'd rather solve because it's not asinine. That one's a little asinine because I'm ignorant about biology. Somehow I ended up with no kids anyway. Maybe that's ignorance in biology. I don't know. All right.
You can do compound interest.
I can do compound interest. I want to do one more example for you. Oh, you'll like this one. What's Newton's second law?
Depends on your definition.
Oh, okay. Yeah, I guess they come in different orders, right? What's the one about acceleration of an object
Mass.
and force and mass?
Yeah, force equals MA.
Force equals so we can take this and we can use this, Newton formed this from observations. This was direct observation, and he also formed it by stealing things from other people, no doubt. And taking their ideas and being a rich dude who took all the credit. But that's okay. If I take an object in free fall, so let's say I just take a ball, I take this marker, just take this eraser. Okay, drop it, right?
Yeah.
How is that modeled by this? Can a physicist tell us?
Yeah.
What's the force acting on this?
Gravity.
Gravity, right? So gravity is the force acting on that thing, yeah? So I know that this, and what is gravity here? Let's use meters and seconds.
9.8 meters.
Yeah, I love it. 9.8 meters per second squared, right? That's the acceleration of gravity. Everybody roughly cool with that?
Yeah.
Yeah, is that positive or negative?
Ooh.
Guess it depends,
I
right?
just got in this argument.
So let's say that x of t equals the height of the object at time t.
Okay, so technically the force is acting in a negative direction, except if you're looking at it in terms of velocity, then it isn't negative. You can't have a negative velocity.
Yeah, I'll buy all that. That sounds pretty good.
So it's traveling negatively.
It is. And we could have a negative velocity. It just depends on the orientation, right? Like if I'm running like this, that's positive, but if I ran back, I'd have to have some way to talk about negative.
And it's like, but it's like the magnitude though, it wouldn't be negative.
Agreed, that's speed. So speed is absolute value of
Yeah.
velocity. Yeah, that's good. That's all good stuff. So if this is x, ooh, help me out here. What's this? What is that of the object at time t? We were just talking about.
I'm losing my definition on the m dot. It's dm over t.
Oh Lord, don't look at that. This is a different example. No.
Sorry.
It's okay. I appreciate you looking at the board, trying to figure shit out. Somebody else help me here. It's not just, Alexander's not the only one here. He can't bear the burden of all this. If x is the height of change, what does this mean that I just wrote here?
dx over
dx dt, yeah, so what is that in other words?
It's the position at time t.
No, this is the position at time t.
It's the rate of change. It's the rate of change.
AKA
at time t.
The
Velocity.
velocity.
Yeah.
This is the velocity
Yeah.
at time t. Yeah, hell yeah.
Totally
Okay.
is velocity.
Okay, here comes, now you ready?
No.
I don't know, yeah.
Yeah, this is the differential equation bit.
Well, we're not quite yet, we're getting there. X double dot, that's second derivative. What is that of this particle or object? What is the second derivative of position with respect to time? Acceleration. This is the rate of change of the velocity. That is called acceleration. So that is the acceleration at time t. Roughly okay, we good? Like once you hear it, maybe it's like painful to cough it up? Okay.
Yeah.
Okay. So that's this A here. That's the acceleration of the object. So if I act on an object with negative 9.8, with the force of gravity, oh wait, that's the acceleration of gravity, right? That's not the force of
That's the
gravity.
acceleration.
Yeah, what is the force? What is force when you're talking about this object right here? What force is acting on it? So gravity's acting on it, but how do I get the force? It's just that, right? Yeah. So this is also called the weight of the object.
Mass.
Right? The mass times acceleration is your weight. It's because everything, this can have a weight here on Earth, but a totally different weight on Jupiter, right? Just because the gravitational force.
But the mass.
Yeah, exactly. So, what we could say here is that the acceleration induced by the force of gravity on an object of mass m bears this relationship. So the force is equal to the mass of the object and its position's second derivative can be inserted for A. And so this force here is just the force of gravity. And what is the force of gravity? Well, the force of gravity on an object is just mg, mass times its the gravitational constant. So notice the m's would cancel here, and I just get this. Long way to really say that any object of position x has an acceleration of negative 9.8 when I drop it. That's a differential equation. And I can solve this one. Let me solve this one for you, because it's one of the few we're going to solve today. So integrate up. This is the second derivative with respect to t. So let's integrate with respect to t. I get negative 9.8 t plus c, gotta have c, equals x dot. So I went up a level. What is c in terms of physics stuff? What is this in terms of physics stuff?
Oh, I don't know.
Velocity?
Yeah.
Yeah. So what is c at time 0? It's the initial velocity. Notice that at t equals 0, that's my initial velocity. So really I could take this equation and go, oh, that's negative 9.8 t plus initial velocity equals my velocity at time t. And the velocity is constantly changing as time progresses because of the acceleration of gravity. This quantity is becoming bigger as time moves along, making me move faster. Now let's move up one last level. I'm going to integrate one more time. So again, I'm going to do integral with respect to t. And this becomes negative 4.9 t squared, power rule. I know you're down in the end, you might have trouble seeing me. V naught times t plus the initial position, x naught. And this is the solution to this differential equation here. And this is also the general equation of motion in space. So I can use this equation to compute exactly where this thing will be at time t if I know its initial velocity. What's v naught if I just let go of it?
The initial velocity is still 0.
0, right? So if I just did my thing, I could get rid of that. I could put in here how high this is. I don't know, how high does that look?
5 feet, 9, 11 inches.
Yeah, I'm like 6 feet, so like, can we say 3 meters?
Yeah.
Yeah, or 2 meters. 3 meters is pretty freaking big. So
9 feet.
plus 2 equals 6. And now I can use this to figure out how high above the ground it'll be at any instant. You might be worried about this giant negative 4.9, but that t is going to be very small. Because how long is this? Half a second?
Yeah, less than half.
Less than half a second. So, differential equation got me here. This is how all these physics formulas are derived. I got one last one for you. One last one. This is a good one. More physics, which is what I understand way more than the bio stuff. I worked with biologists on biological math for quite a while, but I still didn't learn anything because it was just all math. I didn't have to think too much about it. So let's think about one last thing. Have you seen this? Mass spring systems, have you dealt with this in any of your classes? No. This is the good one. This is a great one. This is my favorite. This is one of my favorite Diffie-Q math stories to tell. So this is a mount on a ceiling, and from it I've got a spring, and I'm just going to hook the spring onto the ceiling. So right now, I've got a spring. It's all compact and coiled up. I'm just going to attach it to the ceiling. So it's still compressed. Yeah, and I'm going to pull down on it because I'm going to take a mass. So first off, let's get some things. The length of the unstretched spring is just L. That is the length of that unstretched spring. Then I'm going to attach a mass of M. Mass M. We'll call it M. Its mass is M. It's kind of a nice, works out good. So that pulls down on the spring because force equals mass times acceleration, so it's pulling down on the spring with the force of gravity.
Yes,
Yeah.
yes.
And that's M. So there's a change. It actually expended, we're gonna take the center of mass on this thing. So let's say that that's stretched S. That's the amount stretched. A little bit extra. Cool. So let me tell you a little bit about springs. This spring is a linear spring. So a linear spring, they probably don't exist in reality. Most springs are linear if you don't stretch them too much. But if you stretch them way more than the amount of force required to stretch it, this first inch is different than the second inch. So, but what I mean by linear spring is the amount of force required to stretch it 1 inch is half the amount required to stretch it 2 inches, half the amount to stretch it 3 inches. So I can easily predict how much force is required to move the spring if I know just one of the places it's been stretched by, or how much it's been stretched by. So linear spring here, there's a thing called Hooke's law. You can tell how many times I've told this story, I think, probably. So Hooke's law says that the force required to stretch a spring a certain amount, required to stretch, stretch the spring, is equal to K. This is called the spring constant. The larger K is, the stiffer the spring is. The smaller K is, the flappier the spring is. So let's put this here. Large K equals stiff spring, like a shock or something like that, right? Like a shock absorber. Like you kill yourself with a shock absorber, right? Lose a hand pretty easily.
Not the shock, but the coil.
Oh, the coil. That's like,
Yeah.
so the shock.
The
so
shock is just the absorber. They're not dangerous.
They're like, so that's part of the shock.
Yeah, definitely.
Okay,
Yeah, it's what prevents the coil from just like rapidly bouncing back and forth.
Got it. Awesome. Cool. So that part is pretty tight,
Yeah.
right?
Oh yeah, it's like super
Crazy.
very, very dangerous.
And you need special equipment
Yeah,
to stretch them.
it's mounted on the wall.
Yeah.
Yeah.
Okay.
Yeah.
So large K equals a stiff spring. Times X, and this X is the amount of stretching past equilibrium. X equals distance stretched from equilibrium. So this is Hooke's law, force equals Kx. And again, it's assuming a very simple spring. Most springs are not this simple. But they all are generally this simple if we don't think of big oscillations. So if you think of small stretches, most springs are linear in tiny motion. Okay, so I've got this all set up. I got my spring stretched out, I got my little mass on it, and everything's cool. We're at equilibrium. Nothing's happening. There's no wind blowing. This is at equilibrium. Equilibrium is going to become an important idea for us the next couple weeks. So, what forces are acting on this mass? Gravity, right? And the force acting down is how much?
-9.0.
Yeah, so we'll just say G, right? Because we want to let old people use -32 feet per second squared and stuff like that, right? We want to let old people use their like cubits and the weird shit.
Qubits.
And that's from the Bible. I don't even know what a cubit. I think it's like
A quantum bit?
quantum
computing?
The distance from like Noah's elbow to the tips of his fingers is like a cubit or something like that, or whatever that means. Something weird. Thank God for the metric system. I love the metric system. So this mass is pulling down the spring with a force mg. We know m, we know g. The spring is acting upwards. The spring is trying to pull upwards.
Correct.
So in this direction, I've got the spring force, kx.
Correct.
Yeah?
Correct.
What is this total stretching here? It's just s.
Yes.
Okay?
Correct.
Okay, let me stop. So we're pulling up with a force of ks because of the spring. We don't know what k is. It depends on the spring. And gravity is pulling down. But these two things right here are equal. because we are at
Wait,
equilibrium.
at zero.
Yes.
Yeah, when like you call that your origin, okay.
Exactly. So this is the equilibrium state.
Yep.
Is everybody cool with that?
Mhm.
The forces, if this force was bigger, it would be moving.
Mhm.
If the force of the spring was bigger than this force, it would be pulling up.
Mhm.
So right now, this is the equilibrium condition.
Oh, yeah, yeah,
Sound good?
yeah.
All right. Equal opposite forces, right? Nothing's moving.
Yeah.
So now I'm going to take the spring and I'm going to stretch it. Now I'm going to move this sucker. So I'm going to grab the spring and pull down and move it away from equilibrium. The spring's getting pretty crazy. So remember, this was our equilibrium position right there. And now I'm stretching it by x units. And I'm going to say that a downward stretch is x. So if I pull it down, that's a positive extension. So x equals the extension on the spring. If I compress the spring up, that's going to be a negative compression, a negative extension. So if I push up this way, its position is negative. But we think of this as x equals 0 right here. So if you move down from equilibrium, it's positive. If you move up, it's negative. Now, what in the heck is happening? This system is now in motion, and we have to figure out the equations of motion. And we need to just look at the forces in play here. The only force acting up is the spring force. So again, we've got the spring force moving in this direction. What is the spring force going to be here? And look at all the units. This distance here is x.
Wait, like spring four, like the KS value?
Yeah, so what is the total extension on the spring?
It's S plus X.
Yeah. So the spring force is going to be K times S plus X. Yes. Cool. Because this is the extension right here. Does that sound good?
Yep.
Cool. And then, so that's the only stuff pulling up on it, but gravity's still pulling down. So down this way, I've still got gravity. And that is acting in the way mg.
Yep.
Yeah?
Yep.
Okay, cool. So let's go to Newton's law there. Newton's second law of motion. So the force on the mass, we think about the force F. This is the stuff acting on the mass itself. So I'm going to add up all the things acting on it. I've got the spring force acting, well, first off, I've got gravity acting in the extension direction, so that's positive. And then I have the spring trying to pull me back up with this force. Very dramatic. And then this thing here relates to the mass and its position in the following way. It's the mass times the acceleration of the object. So these forces are inducing an acceleration on the mass in this way. So let's take this and rewrite it, make it pretty, and you're going to see something beautiful. All right, so we've got mx double dot, I'm just going to copy it down again, mg minus k times the extension sx. Cool. Let's simplify over here. So we've got mx double dot equals mg minus ks minus kx. Does anything simplify?
Okay.
Ooh,
Oh, wait, we're subtracting it, yeah. We're good.
you were, I'm sorry, so what do you, we're hearing k, what do you mean by k? Not that there's, k is definitely involved in what I'm thinking of. Let me ask it more clearly so you know what I'm looking for. Does anything cancel?
And mass, it's always mass.
It wouldn't cancel out of these guys though, right?
Oh,
Yeah, okay.
alright.
Is there any two quantities over here that cancel? Look at the setup. Go back to equilibrium. I wrote an equation.
I was
of
about to
the
say
word.
at the center,
Yes.
the K and the KX, or the KS, like you're not gonna have S plus X. It's just the KS is equal to KS. At
The
the
Ks is equal to mg.
Yeah, that's what I meant. Oh,
Yes.
at the center though.
Yes.
At equilibrium.
Exactly. When this thing wasn't in motion, the restoring force was equal to the force of gravity. Ks equaled mg. So that's still true here. There's no variables. These cancel. And so I've got mx double dot equals negative kx. I'm going to move everything to one side. Mx double dot plus kx equals 0. That is a differential equation expressing the motion of a spring of mass m and spring constant k. That is pretty cool. So now if we could only solve that, we're not going to be able to, I'm going to tell you how to solve that in this class. This is DiffyQ. Take MT360B if you want to learn how to solve this. I'll give you some hints at it, but it's kind of a whole theory. Every differential equation usually comes with initial conditions. So we're going to say x at 0, at time 0, is the initial position. We're going to say x dot at time 0 is the what?
Acceleration.
Force. V. Velocity. V naught. Right, change of position.
Oh, yeah.
Yeah. Does that make sense?
Velocity and position.
Yeah,
Okay, yes.
exactly. And then the equation itself relates that. Let me show you how this might work. Let's say we work this all through and we've got, example. We've got a mass of 1 and we've got a K of 9. So this differential equation, so this is the restoring force of the spring, this is the spring constant, this is its mass. Pick your favorite units. I don't want to think about it. So the equation of motion for the spring is this. So I plug those in, so it's x double dot plus 9x equals 0. And I could have some initial conditions here. Let's say that, and the initial velocity is none. So this means that I took the mass and moved it down 1 unit and didn't add any upward force or downward force when I pulled it down. So this is saying an extension of 1 downward, which now moves me off equilibrium, so stuff will happen. We're off equilibrium. And if I added velocity, that would be me like pushing it down or like moving it down and then shoving it up or something like that. So there's no initial velocity. I'm just going to tell you that the general solution to this, so the general solution, we have, I won't incorporate those yet, is going to be x at time t is some constant times cosine of 3t plus c2 times sine of 3t. Is that even surprising at all that the solution would involve those trig functions? And tell me why not. Why is that not super surprising? Yeah, because oscillation, exactly. We oscillate. And there's notice I haven't talked about friction or anything. So it's very unrealistic. I didn't talk about friction. If there was friction, this thing would have to die out. This will not die out. So this is an unrealistic solution. It's a zero friction lifestyle. But we can go to those initial conditions. The fact that x at time 0 has to be 1 says that when I plug in 0 here, I have to get a 1 out. So that would mean that C1 would have to equal 1 because cosine of 0 is 1. Sine of 0 is 0, as you know from your sheets with this shit all over them. And then I could find x dot, so let's do that really quick. So first I take the derivative, it's going to be negative 3c1 cos sine 3t plus 3c2 cos 3t. And when I plug in 0, that has to give me 0. Well, I already know c1, but when I plug in 0 here, this part dies anyway, and I've got 3c2 times 1 cosine of 0. That must equal 0. So it looks like C2 equals 0. So the solution to this problem right here, that spring, is x of t equals cosine of 3t. And if I sketch that out, I would know the position of the spring at any instant. And I could even find its velocity and all sorts of stuff. But we now completely understand that mass spring system. We can do lots with it. Take Diffie-Q. You're going to be so happy. Take Diffie-Q. None of you look almost, these are the only two folks that look happy in here right now. And it's only one of you that looks really happy. Okay. now okay, good. So let's do, I want to make sure you've got enough to kind of get rolling on your homework. Hey, could you, does everybody have their laptop with them today? That was cool. Let's get our laptops out and, what's up? Yes, yeah. Oh, I love that you were even looking in there.
Is that the, yeah.
Yes, sir, yeah. There's an app in the announcements in World Class that I'd like you to open up. You can do it on your phone. It'll be fine. I wanna start understanding differential equations visually. And so we're gonna do some experiments here. Good Lord. Why can't we have electronic boards and I just push a button and it saves the board and clears it? God. Yeah, smart board. Do they have those anywhere in Regis?
No, I've
Just-
never seen.
I've never seen. We only got dumb boards, and they're not even good ones.
True.
Dumb word.
Dumb board. I want a chalk dumb board, like in my office. Now that's a sweet board. All right, let's take a bit to narrow our focus. We're going to narrow our focus to a very specific type of equation right now, and it's going to be of this one: y prime equals some function of x and y, or with same rhythm, different variables, x dot. Now remember, this means derivative with respect to t, the prime means with respect to x, so I better remind you of that. This is dy dt, this is dx dt. They're both just rates of change. It's no big deal. This one can be interpreted as velocity because it's with respect to time. And that is equal to some function f of independent variable and dependent variable. So we're going to focus on those guys. So this is saying, I want you to really understand what the heck this means. This means that the solution to this thing has the following relationship. I can find the tangent slope to a solution at any point. So this is tangent slope to a solution at point xy. And this is the formula for giving you the slope of the tangent at any point. That's just all it is. If I say to you, hey, here's the function, find the slope at 2, 3 of whatever solution we have, you just plug them into this expression and get a number out, and that's your answer. Same thing down here. This is the tangent slope, this is the velocity at tx. So here, let's do that. This is the velocity of a solution at point tx. So rate of change, state, rate of change, state. So let's look at a very simple one. Y prime equals y. Let's just start there. And if we can understand this, you've actually understood a lot. That looks simple, that is not simple. So this is saying any solution of this thing, its derivative is equal to the function itself. So let's think about that first. Just write out a few things to think about here. Any solution to this differential equation, Diffie-Q, has the property. I'm going to write this a couple ways. First property is the derivative of the solution, the derivative of solution y of x is equal to the y of x equals y of x itself. What's that?
I was just saying y
Oh, cool,
equals
cool.
y.
Yeah, exactly, yeah. Can you just think of a function whose derivative equals itself just really quick?
E to the x.
Yeah, e to the x, right? So we already kind of know the solution to this. I'm just going to tell you that right now. So we can know just by observation. By observation, we can see that y equals e to the x solves this. Does that sound reasonable? Do you see what I mean by solve? If I take this function and I find y prime, and I plug it in on this side, and then I plug in the formula for y on this side, I get the same thing.
So you're just like establishing a relationship with e to the x?
Yeah, I'm just saying for this particular problem right here, e to the x is a solution.
Oh, it's not, I thought you were saying we can use that to solve this relationship.
We can.
Oh, okay.
Yes, that's exactly what I'm saying. Yeah. But just this one, not in general. Just this very particular
Gotcha.
thing I've written.
Yeah, okay, yeah. So does that imply that specific relationship or equality that you've written up there, it can be bigger and still mean the same thing? Like,
It
more
can be-
things involved with it? other than
It
y?
wouldn't mean the same thing if I wrote it differently. It would be a different relationship. Yeah.
Okay.
In fact, how about this? If I say y equals some constant times e to the x, that is a solution no matter what c is.
Right.
Do you see that?
Yeah, that makes sense.
No matter c. Because its derivative is itself. So this is one way to look at this. I'm going to show you a different way. I've shown you a bunch of different ways to look at these, but here's one of the most informative ways. And looking at it this way will help you understand how a computer will solve a differential equation. So another view, a geometric view, and this is what I want to spend some time on. A geometric view. That's what that app is going to be for. So these are called direction fields. Or you can vector, it's not really a vector field, direction field, sometimes slope field is used. And what it means is I'm going to understand all of the solutions at once. I'm going to understand them without even solving the problem. I'm going to understand the nature of the solution. So I come here, I make a little plane, I've got x, y, and I've got my differential equation. Y prime equals y. So if I pick a point in the plane, I want to kind of go through mentally and pick a bunch of different points and find the slope there. So what is the slope of the solution? What is y prime when I'm at 0, 3? What is y prime?
0, 3. Oh, at what?
What is this? How does this say to take, you take the xy coordinates, grab the y coordinate, and that is your slope. So look at this equation. It's saying to find your slope, all you need is the y coordinate.
It's just 3.
It's just 3. What is the slope of any solution that goes through the point 1, 3?
3.
What's the y coordinate? Still 3, not changing.
It's just like,
What is, let's do another one. How about that point? What's 3? So it doesn't really matter what x is. If y equals 3, the slope is 3. So all along the line, y equals 3. I'm going to get a different color out. I've got little lines of slope 3. And that's pretty steep. So like slope 1 is perfect diagonal, so they're pretty steep. I'm going to put these little arrows. And that means when I cross that line, that's the velocity and direction that I want to head. So you can think of these as velocity vectors. As you cross this line, your curve has to be tangent to those vectors. Ooh, I like that. Wow, I love that. Indeed. So what about at 0, 1? What's y prime?
1. Oh, wait, yeah, 1.
Yeah. Do we all agree that along the line y equals 1, the slope is 1?
Yeah, that really makes sense.
Awesome, awesome, oh my goodness. So all along this line, y equals 1, the slope is 1. And that's mellower. This was m equals 3, this is m equals 1, so it's a little chiller. This, look at that, do you see a flow?
Yeah.
There's a flow starting in the plane. And we are going to understand the entirety of this flow. So let's go one more space, or one more point. What happened? Oh, sorry, was a question? Comment?
No question, comment.
Okay. If y equals 0, what's my slope?
0.
0. So all along the x-axis, the slope is 0. This is a super important point. All along the line, so this was y equals 1, this is y equals 0. All along there, the slope is 0. I know it's getting a little old, but I'm just going to keep doing it. All right, let's look underneath. What happens when y equals -1?
Like 0, -1. Y
Yeah.
prime.
When y equals -1, what's my slope?
It's gonna be -1. It's gonna be like
Does that sound good?
Yeah.
-1? So m equals -1. Cool. What happens, let's talk now. What happens to the slope as the line moves up this way?
It gets like
Straighter, almost straight up, right? It'd be really hard to draw the ones up here. So if I was up even a little further, I've got to somehow make it look steeper than a slope of 3. It starts to look kind of vertical. It's a little tough.
Can it go further than that? Like, as in like. That makes sense?
No.
So it can only get vertical, more and more vertical. Like it can't go.
Yeah.
vertical.
Yeah. Oh, it wouldn't. Oh, I see what you're saying. It wouldn't flip over. I'm not going to say that.
Alright.
I'm not. It could.
Okay.
I think I could come up
In
with
this
it.
example, no.
In this example, no.
Okay.
This is.
I think I actually get what you're saying though. By like, it just gets infinitely more vertical, even though it's not. Like,
Yes, that's a beautiful way.
Yeah,
to say
yeah, I
it.
got you.
Well, what's happening on this line?
Same
That's
thing, but
lower?
negative.
Negative. More negative. Yeah.
Yeah.
Okay. So now here's the slope field representing our differential equation. Think of this as like an air hockey table or a pond, and these are the currents.
Yeah.
This is how things will flow. So if I come into this air hockey table and I put a puck down here, same damn color, I was hoping for a new one, and I put a puck down here, it's right away going to travel in that direction. Immediately. That's the velocity vector. So it immediately travels this way. But as soon as it moves away from that line, the velocity vector starts changing.
So does that go like straighter?
And it and it has to be consistent with it. When it crosses up here, it has to have that slope.
You can create like a parabola.
Kind of parabola.
I get not a parabola,
Like an E.
like an E is what I was gonna. I almost said natural log, but
Like an E. Like an E. What happens is I move this way.
negative.
Right, so what happens between here and here? It's kind of a flatter slope in here, right? More like a half or something. So what I get is that asymptotic behavior. I can't actually get onto here because every time I drop down, there's another one that's like going, no, just keep going that way. Keep going that way.
I have a question.
Yes, sir.
So if you're suggesting like the negative direction of that example you just said, but is that even like possible if the velocity vector is always going to be pointing in like the positive direction?
Yeah, we can think of just backwards time. That's all I was thinking.
Okay.
The reverse time.
But
So
so it is possible if it was. I mean, I guess like obviously the world doesn't restrict where things can move, but do you see what I'm asking?
Say more.
Well, because you're drawing your velocity vectors
yes.
or just your slope at that point
Mhm.
as up and to the right, which is
Yeah.
positive in both directions,
Yes.
x and y.
Right.
So if you're moving it negative, like is that even possible since that at that point?
Oh, I gotcha. Not with this kind of equation.
Okay.
Yeah, we won't see arrows pointing down and left or up and left.
Okay,
Yeah, that's a great.
okay.
We're always gonna assume this rightward flow on our arrows. What happens if I place the hockey puck on the x-axis?
It'll just keep going on 0.
Just stays at 0. It doesn't change, right? So if at some point y equals 0, y is always 0. What do we call that in physics or chemistry?
Initial, or rest, at rest.
Origin, definitely origin. What do you call it? We already used the word, sorry, I'm always guessing.
Baseline.
Equilibrium is the word I'm looking for.
Oh.
So if something doesn't change, it's at equilibrium.
Oh, that's why the science thing.
Yes. So notice here that y equals 0 is an equilibrium solution. Because it never changes. What happens if the puck's a little below the y-axis?
It'll go left, like down,
Do you see it cruising away?
like left and to the
Yeah.
right and down is what I'm.
Just like that, yeah. So now check this out. This is an equilibrium solution, but if you were to have a slight bit of noise in your system, so you got your leaf on the pond floating along here perfectly, any slight veering away from there either sends you up this way or down this way. If you fall off of that equilibrium path, you're gonna rocket away, either up or down. That is called an unstable equilibrium. Let me show you what I mean, and then we'll call it a day, and then we'll come back in. So, I love stacking pens. We'll see if I can do it. Literally see if I can do it. Like, literally stack them. Oh, there we go. These are all the same kind. So, this is almost modeling something like this. This is at equilibrium, right? So that's it. But any slight perturbation sends it careening to either side, right? So this is equilibrium, but it's unstable. It's so bad. But this is equilibrium that is stable. I approach it. So check it out again. We're going to play with this idea. Unstable equilibrium means a small perturbation sends it away from equilibrium. Stable equilibria, we return to them over time.
In this case, though, there's no stable equilibrium, right? Because
That's right.
you can't.
That's right, yeah. That is just an unstable equilibrium. And there's only one equilibrium.
Yeah.
So in the homework, you're eventually going to see some equations, and they're going to give you this, and they're going to say, find the equilibrium solutions. And what you're going to do is you're just going to find, i.e., where is the slope 0?
Equilibrium slips.
No change.
No.
No change in state. Let me give you a really quick, I said I lied. I'm going to show you one last one. You know what? I see people falling asleep. I'm going to stop. People are getting sleepy. Not naming names. I see some sleepy people. So, let's come back in on Wednesday, refreshed. Maybe check out the web work. Just the first 3 problems are all you should work about right now. The first 2 are volumes. And I'll also collect your assignment from you, please. You gave me yours. Yeah, we're good. So if you didn't give it to me on Friday, I got yours. Yeah, and I got it. Yeah, I got it. Yes. I got to hook you up, my friend.
I had to go get a snack, bro. I was like,
I don't know where, you just sent me to I was like, oh,
that's my bad.
yeah, I had a long weekend.
Now I'm gonna have
That's
to
why I'm
mail
not
it
going
to
to
you.
work.
I gotta run my chemistry lab.
For tomorrow?
No, the post lab from 2 weeks ago.
Oh, thank you. Thanks, guys.
It wasn't,
Thank you.
it didn't end up being the last Wednesday because we, membership
Let me
came
show
out
you
last
what
week.
it is.
So the lab department, the distillation lab.
Yeah,
I'll send you a PDF.
Isn't due till today.
Yeah.
And I
This is
I
someone else's,
successfully
otherwise
took all
I
2 weeks to
this is
procrastinate it. But
Oh,
I
it's
wrote my
basically
procedure
take
during
this
the lab
region,
for
yeah.
once this time, so I shouldn't, I
Sketch
think I
it.
don't really have to do anything for it.
Then
It's
just
not a lot.
set up-
I know, this was a really short lab, because remember we just sat there and waited
And if
30
you're-
minutes
if
for
you-
things to still.
I think tomorrow,
so
we
if you
might get a
have-
lot
you let me know
super
first.
early. Cause we're gonna
You
be
will
talking about the
be
meds.
IRMR or whatever, it's not even
No.
experiments,
Will
but
you?
it's fucking
Okay,
lab
alright,
work, I
good.
mean,
No,
So,
we're gonna
let
be
me know if
talking
you wanna
about
go
the
through any
next
of
thing.
this.
Yeah,
It's
I
not
know.
like
Are you
one
using
specific
free,
one.
like,
No, I know,
full
and
class
it's
with your
not-
class
it's
for
not-
this?
they're not even experiments either, they all happen in,
Okay.
it's all like
I'm in my office.
yeah, infrared stuff.
I have an appointment. Maybe it's next
We're at a
week.
state police on this.
You don't need to put this in.
Yeah.
Oh, I see.
Oh, okay. So if you wanna talk, just come on by and I'll help you out. But I'll email this and maybe you get it to me by Friday? What's that?